Our second lecture in the Understanding Deep Learning seminar series. Our speaker today is Jascha Sohl-Dickstein, who's a senior staff research scientist in Google Brain and leads a research team with interests spanning machine learning, physics, and neuroscience. He was previously a visiting scholar in Surya Ganguly's lab at Stanford and an academic resident at Khan Academy. He earned his PhD in 2012 in Bruno Olshausen's lab in the Redwood Center for Theoretical Neuroscience at UC Berkeley. Prior to his PhD, he spent several years working for NASA on the Mars Exploration Rover mission. Jascha, please take it away.
Thank you. Thank you so much for the gracious introduction and for inviting me. I'm excited to be here. So before I actually start talking about what I'm here to talk about, I want to very briefly advertise for another project that you might be interested in and that we're soliciting contributions for. So you may have heard that recent large text models like GPT-3 have started demonstrating some really amazing capabilities. These models have also more or less saturated performance on the existing benchmarks we have for measuring the capabilities of language models. So to address this, we're developing a new collaborative benchmark to quantify the capabilities of text-based artificial intelligence systems. I think to me, more importantly, also to try to extrapolate what their future capabilities will be. We have submitting a task to this benchmark is quite lightweight. Many tasks can be defined just using plain text. And as an incentive, if you contribute a task to the benchmark, you also become a co-author on the paper announcing the benchmark. So this is perhaps an unusually direct way to get a high citation count paper or increase your H index by one. You can kind of think of the goal of this project as being to develop a diverse modern-day Turing test. And so as diverse tasks as you can think of are strongly encouraged, and we're especially interested in tasks from fields outside of machine learning, like philosophy or neuroscience or physics or linguistics or math. So if you have ideas for tasks, you should consider submitting them to BigBench. I think it will be an exciting and extremely useful benchmark. Also, non-English tasks are encouraged and recommended and currently underrepresented. Okay, so advertisement over. Now I'm going to tell you about the large width limit of neural networks. Please feel free to ask questions, which I guess is going to happen somewhat indirectly via the live stream during the talk, and I will answer them as I go. There's a few bits in the middle that are quite dense, and getting questions is a really good service to me because it helps me understand when I have not expressed something clearly. And I promise you, if you have a question, then many other people do too. So it turns out that as neural networks become wider, they both perform better and become more analytically tractable. And in fact, in the limit of infinite width, you can often abstract away the parameters of the neural network entirely and make, I believe, like really surprisingly strong closed form statements about the behavior of the network. And so I'm going to tell you about some work understanding neural networks in this overparameterized large width setting. I'm going to talk about a large amount of work done by a large number of people. I'd especially like to call out the subset of them listed here, each of whom was a primary contributor for more than one of the results that I'll be presenting. Just reading the names off, there's Yasmin and Roman and Jehoon and Surya and Jeffrey and Sam and me and Lei Chao and Greg and George. So why are overparameterized networks an interesting object to study? Basically because they do better. There is a history in machine learning of building larger and larger models and getting higher and higher accuracy. Even within a given model class, though, test accuracy increases with increasing model width. So here we're showing experiments supporting that improvement with width for both fully connected and convolutional architectures, in both cases applied to CFAR10. So every point on the fully connected plots on the left corresponds to the same architecture and the same depth, but different settings of training and initialization hyperparameters and different widths. In both plots, only models which achieved 100% training accuracy were kept. So here, a generalization gap directly corresponds to test accuracy. You can see that if we take the best hyperparameters at each width, then wider models strictly outperform narrow models on test accuracy out to a width of 20,000, which was as wide as we could go with our memory constraints at the time. Similarly, in the right plot, each line corresponds to the same convolutional architecture defined in terms of number of layers and nonlinearity. And for each point in the plot, we're taking the training and initialization hyperparameters that did best on the validation set. You can see that for comp nets with pooling as well, accuracy strictly increases with increasing width, once again, out to the widest networks we could practically build. So these observations that we do strictly better with increasing width raise maybe the question, what happens in the limit of infinite width? In this talk, we're going to examine this infinite or large width behavior of neural networks. We're going to do this both for Bayesian neural networks and for networks trained by gradient descent. And although for reasons of narrative flow, we're mostly going to focus on the Bayesian networks. We're also going to characterize this large width behavior both in parameter space and in function space. So to start with, let's examine the distribution of our functions induced by infinitely wide neural networks. Not to spoil the punchline, as I spoil the punchline, but we're going to find out that infinitely wide neural networks for most common architectures are equivalent to a Gaussian process. I also want to call out here the link to the neural tangents library that I give in the middle of this table. This is a neural network library built, especially Roman Novak, Sam Schoenholz, and Liqiao Zhao, which enables infinitely wide neural networks to be constructed and used as easily as finite width networks can be. So if this turns out to be an area you want to pursue further, this is an invaluable tool for doing research on infinite width networks. So, okay, zooming in to the upper right square here. To see why neural networks might be described by a Gaussian process in function space, let's look at the distribution of our functions induced by randomly initializing a simple fully connected feedforward architecture. So this architecture has inputs Y0, pre-activations ZL, and activations YL. The pre-activations ZL are an affine transformation of the preceding activations with weights WL and biases BL. Both, as you can see on the right, both the weights and biases are initialized by draws from a Gaussian with variance sigma squared W divided by width for the weights and variance sigma squared W B for the biases. The network's outputs or logits are Z capital L. And for simplicity here, we're going to assume that the output is 1D. And so that Z capital L is a scalar, and N capital L, it's the width of that layer is equal to 1. And here, all the weights and biases together, all the W's and B's together are called beta and are the parameters of the neural network. And so we're going to be examining the distribution of our network outputs Z capital L induced by randomly initializing this network. I'm going to leave this little cheat sheet about the network architecture in the upper right for a while. So before we dive in mathematically, let me illustrate visually what the core result is going to be using a simple cartoon. So this plot compares the network's output or logit Z capital L for two different inputs, X and X star. If we draw a sample of the parameters from their prior P of theta and compute the output of the neural network for these two inputs for those parameters, that will correspond to a single point on this plot. If we reinitialize the network parameters over and over again and plot the outputs for each initialization, then we'll get a distribution over network outputs for these inputs, or equivalently a distribution over functions computed by the neural network, which is induced by the distribution over parameters. The core result in the section is going to be that as the hidden layers of the neural network become infinitely wide, the distribution over functions converges to a Gaussian process. And so the distribution over neural network predictions for any set of data points becomes jointly Gaussian with a particular compositional covariance kernel that it turns out we can compute. I'm going to just pause super briefly here. Are there any questions about the cartoon version of what we're about to try to show? Okay. So.
No questions to now.
Yeah. Hello?
No questions until now.
Okay, sorry. Great. Awesome. Okay, so let's dive in mathematically. First, as a brief refresher, what is a Gaussian process? You can think of a Gaussian process as being a Gaussian distribution over functions. So a Gaussian process is a stochastic process over some continuous domain of random variables, such that for any finite collection of those variables, the distribution is described by a multivariate normal distribution. So for instance, in our case, the distribution over network outputs for a set of n input examples is going to be jointly Gaussian, with mu providing the mean of that Gaussian over network outputs, and the number of data points by number of data points covariance matrix K describing the covariance of that Gaussian. If you've seen GPs before, you are probably most used to seeing them plotted as draws of functions over a 1D domain. For instance, this plot in the lower right shows several draws from the Gaussian process corresponding to a particular neural network architecture. From this perspective, the plot I showed on the previous slide would correspond to plotting sample values of network outputs, the Z capital L, against each other for two different inputs examples, X and X star, where here X and X star are just two different values of the X-axis. These are just two different ways of visualizing the jointly Gaussian distribution over functions induced by a Gaussian process. Okay, so now that I've told you what the result is going to be, let's work through a sketch for why it's true. The derivation I'm about to work through, or the derivation I'm about to give a high-level picture of, is closest to that in Roman and Lechao's ICLR 2019 paper, which is the bolded reference in the lower right. So first, we know that the pre-activations, ZL, are a weighted sum of Gaussian random variables corresponding to the weights and the biases of the neural networks, where the coefficients for each of those Gaussian variables are the preceding activations. So this means that the ZL are a Gaussian process conditioned on the preceding activations YL, just because they're the sum of a bunch of Gaussian variables, and the sum of Gaussians is still Gaussian. People sometimes get a little bit confused about this, so I would like to emphasize that the ZL are a Gaussian process because the weights and the biases are Gaussian. We're not assuming activations in the previous layer are Gaussian, and we haven't yet taken anything to be infinitely wide. This is true even at finite width. The covariance or kernel of this Gaussian process depends on the second moment matrix or gram matrix KL of the preceding activations YL. That is KL, x prime, is the covariance between the activation vectors for x and x prime at layer L. Here you can see that the weight scale, sigma squared W, just changes the overall magnitude of the covariance matrix of the Gaussian process describing Z, while the bias is shared for all inputs to neural network X. And so increasing the scale of the bias tends to make data points more similar to each other, and thus makes the covariance matrix more like a constant matrix. Because KL is the covariance matrix before the affine transformation, you can view this as relating the covariance matrix between examples after a random affine transformation to the covariance between examples before the transformation. In practice, we are going to compute the covariance matrix KL for all pairs of data points. And so KL will, when realized, be a number of data points by number of data points second moment matrix. Okay, so that is step one, which states that the pre-activation ZL are GP conditioned on the preceding activations YL. Now for step two, we observe that ZL only depends on YL through its second moment matrix KL. Because of this, we can say that ZL is a Gaussian process conditioned on the second moment matrix KL rather than conditioned on YL. Just for reference, you can see that I've added the equation for the second moment matrix on the right. Cool. Okay. So now after step two, we can say that the Z's, the pre-activations, are a GP conditioned on the covariance matrix from the preceding activations. This build right here is going to be the mathematical high water mark of the talk. So this slide will both be an excellent place to ask questions, and also it will get easier from here on in. So this is also a good place to make sure you understand at least the core ideas that I'm expressing. So K0 is by definition just the data point by data point second moment matrix at the input layer. KL for L greater than 0 is the second moment matrix of YL, the activations at layer L, which is computed just by averaging over units I in layer L. However, YL is the activations after applying the network nonlinearity phi, where phi could be like ReLU or tanh or some other nonlinearity. And so we can substitute phi of Z L minus 1 into the equation for the second moment matrix KL. So we just here rewrote YL in terms of the preceding pre-activations, Z L minus 1. From step 2, we know that Z L minus 1 is a Gaussian process conditioned on K L minus 1. This means that KL is just an average over NL units, where each of the units is a draw from a Gaussian process. As NL goes to infinity, as the width of the layer goes to infinity, a concentration of measure style result applies. And we can replace this average of the inner product of units for pairs of examples with an expectation over the distribution generating the values of individual units, where these are, where again, the individual unit values are draws from a GP. The value of the expectation is deterministic though. This means that in the limit of infinite width, the second moment matrix KL at layer L is a deterministic function of the second moment matrix KL minus 1 at layer L minus 1. Awesome. And for simplicity, we will write the deterministic functional, which transforms KL minus 1 into KL as F. So we can say that the covariance matrix KL at layer L is just F applied to the covariance matrix KL minus 1 of layer L minus 1. For many common architectures and nonlinearities, we can compute F analytically. And even when we don't know how to compute it analytically, in most scenarios, it only requires solving a 2D integral because it only depends on x and x prime for every pair of inputs. And so we can typically efficiently compute this numerically. For instance, there's code that allows you to do this as part of neural tangents. All right, I'm going to pause for like 10 seconds here and see if the core idea behind this slide makes sense to folks. Again, this is the mathematical high water mark. So this is a really excellent time to ask questions if you have them. Okay, cool. I will continue on, but feel free to ask questions at any point. So finally, to get the correspondence of wide neural networks to Gaussian processes, we just put these last two pieces, we just glue these last two pieces together. So we know from step 2 that the top layer logits are described by a GP given the second moment matrix K capital L of their preceding Y capital L. In turn, each of the second moment matrices are deterministic functions of the second moment matrix from the layer below in the limit of infinite width. So what this means is that the top layer logits are a Gaussian process conditioned on the second moment matrix of the inputs and thus conditioned on the inputs. This GP has a particular compositional kernel or covariance matrix, which can be found by applying F to the input kernel L times in a row, which we write as F to the capital L here. And then accounting for the variance of the readout weights and biases, which contributes to sigma squared W and sigma squared B term. So the distribution over functions computed by a neural network at initialization is described by a Gaussian process with a particular compositional kernel, which we know how to compute. I think this is a fairly remarkable result in that it gives us a closed form, super simple expression for what the outputs of a neural network will be and what the distribution will be. So what can we do with this new understanding? First, we can maybe observe that a neural network at initialization corresponds to the beginning of neural network training. So if we can understand the properties of the neural network at initialization, it allows us to make strong predictions for whether the network will be trainable. Second, this result holds more generally than just that initialization. It holds, in fact, and generally for Bayesian neural networks. And as we'll discuss, for Bayesian neural networks, this also lets us get a closed form expression for the posterior prediction on test points. Yeah, awesome. Okay, so there's a question here, which is how does a nonlinearity impact the kernels from deeper layers? And the answer is that the kernel is a function of the nonlinearity. So if you change the nonlinearity, then the mapping from the kernel layer L-1 to the kernel layer L changes. There are conditions for the neural network to continue to be described by a GP, but they're relatively mild. There are things like the variance after you go through the nonlinearity needs to still be finite. Like I think the nonlinearity needs to be smooth and yeah, I don't remember the full set of technical conditions, but there's relatively weak technical conditions on the nonlinearity, which are satisfied by all common nonlinearities. So next question, what are examples of layers which we don't know how to compute the kernel for? So it's a relatively small number of layers where we know how to compute the kernel analytically. So for instance, we can do this for error function kernels, error function nonlinearities, which look a lot like tanh nonlinearities, but are totally different. And we can compute it analytically for ReLU nonlinearities. However, for nonlinearities where we cannot write down a closed form expression for the kernel, it typically involves only solving a two-dimensional integral. And you can see this in that you can see that we are only really interested in functions of two input points at once in most situations. Batch norm maybe being a really difficult situation where you have to consider all the inputs at once and the integral you have to solve becomes super high dimensional. But in the absence of batch norm, it's typically only a 2D integral, and we can just solve that numerically even if we don't have an analytic form. And finally, time complexity for this procedure. You have to compute the kernel for every pair of data points. So the time complexity is quadratic in your data set size. And of course, linear in network depth, because you have to, of course, compute this serially for every layer of the network. Cool. Okay, so talking about what we can do with this understanding that the distribution over functions computed by randomly initialized neural networks becomes a Gaussian process at the large width limit. So let's start with predicting trainability. So in order to evaluate trainability and initialization, we can look at what happens to the covariance matrix K as the network becomes deep. The evolution of K with depth is a recurrent process. We're just applying F to K over and over and over and over again. One common behavior of recurrent processes is that they converge to a fixed point. And generically that they tend to decay towards this fixed point exponentially. This is in fact what happens here. So we can write K capital L in terms of a fixed point K star, which is like the covariance matrix that the network will have if you just make it infinitely deep, plus a term which decays exponentially with depth over characteristic depth scale, which here we call chi-c. So in order to understand trainability, it turns out, and you'll see why in a moment, we can examine how this decay towards a fixed point changes as a function of the initialization hyperparameters, sigma squared W and sigma squared B. So here we're going to illustrate this for a fully connected network with tanh nonlinearities. If you have a background in physics, this is like super similar to mean field style analyses in physics with like accompanying phase diagrams. So when sigma squared B is large, when the scale of the bias initialization is large, the shared bias vector causes dissimilar inputs to converge and become more similar. And the fixed point corresponds to activation vectors for all inputs becoming identical, with constant covariance matrix entries, of course, because if you have if all inputs are identical, then the covariance between any pair of inputs is the same. On the right side, on the other hand, the tendency of large weights to push apart initially similar inputs dominates. And similar inputs are made increasingly dissimilar with depth, as captured by the scaled identity contribution to the covariance matrix. So these two behaviors induce ordered n-chaotic regimes, where all inputs either become identical with depth in the ordered regime, or where initially similar inputs become pushed apart, and the network essentially acts as a hash function in the chaotic regime. This talk so far has focused on forward propagation of activations and the distribution over network logits being a Gaussian process. However, gradients are linear operators, and a linear transformation of a Gaussian is still a Gaussian. Subject to some weak constraints, the same is true of a Gaussian process. So if a function is described by a GP, then its derivative will also be described by a GP. This means that it turns out we can do a nearly identical analysis of the input-output Jacobian of the network as we did for the forward propagated activations. When we do this, we find that in the ordered phase, the Jacobian norm goes to 0, and gradients therefore vanish. In the chaotic phase, on the other hand, because small changes in inputs cause large changes in outputs, the Jacobian norm goes to infinity, and gradients explode. And of course, you can like think about this for a minute and see this has to follow from like the definition of gradient, in that if you change the input and the output doesn't change, that must correspond to a gradient of 0. And if you change the input an infinitesimal amount and the output changes a very large amount, then that must correspond to a gradient norm going to infinity. Both of these behaviors are pathological and make training deep neural networks impossible if the gradients are exponentially large or exponentially small. If you stare at this diagram for a minute, though, you're going to notice that there is a line right down the middle where something different must happen. Along this critical line, the two tendencies perfectly balance. There, k does not exponentially decay towards a fixed point, and the gradient does not exponentially vanish or explode. So maybe as a hypothesis, it seems plausible that in order to train an extremely deep neural network, this line where the gradient remains well conditioned with depth would be a good place to do it. Let me just pause for like 15 seconds here and see if there's any questions. Okay, cool. I'm going to continue. So the hypothesis is that This critical line is a really good way to initialize your neural network if you want to train a very deep neural network. Here, this critical line corresponds to particular choices of initialization scale for the weights and the biases. And in fact, we find that to be true. So here we train vanilla convolutional neural networks with no residual connections, no batch norm, none of the other usual tricks or techniques used in very deep networks. We do this with an initialization carefully chosen to lie on this critical line. We also chose the initialization to satisfy another property known as dynamical isometry, which demands that the Jacobian spectrum be well conditioned. But I'm not going to talk about that today. By doing this, we are able to train convolutional neural networks up to depths of at least 10,000 layers with near identical train and test curves as for shallower networks. This is orders of magnitude deeper than have been achieved with vanilla convolutional architectures before this work. Cool. So this is neat in that here we have like a theoretical model, and it turns out to produce a practical formula, which allows us to better train neural networks. I've just shared either results or analysis for fully connected and convolutional networks, but similar approaches can be applied to analyze most common architectural components. I'm not gonna go through all of these, but let me briefly tell you about a couple results where this style of analysis maybe provided some surprising insights. So here in this slide, we're looking at an analysis of the effect of dropout on trainability. So each pixel in this image corresponds to a network of a specific depth L, initialized with a specific weight scale sigma squared W. And the color of the pixel corresponds to the achieved training accuracy, where redder corresponds to higher accuracy. Just a question, which, give me 1 second, please. Yeah, so the answer, so the question is, the phase transition shows a very strict constraint on the initialization. Is this the case in practice? And the answer is it depends on the network depth. For shallow networks of like 3 or 4 layers, then the exact initializations don't matter very much. But if you want to train a neural network of dozens, like probably of greater than like a dozen layers, then getting the initialization right on the critical line matters more and more and more. And for very, very deep networks, it's completely crucial to success. So I was describing this diagram. I think the dashed line here is our prediction for maximum trainable depth. It's the characteristic depth scale chi-c. Maybe surprisingly, you can see that in the presence of dropout, there is no critical line. So even as you change the weight variance, this plot, by the way, is for a fixed value of sigma squared b. It's like 0.1, I think, but it doesn't matter too much. Surprisingly, there is no critical line in the presence of dropout, and the maximum trainable depth is always finite. Qualitatively, maybe you can imagine that what happens is that dropout erases a fixed fraction of the information about the input with every layer, such that information about the input decays exponentially towards 0 at depth, making training impossible. This is probably suggestive for why dropout is super effective for shallow neural networks or on side chains and ResNets. But like completely fails if you try to do it, for instance, in a recurrent path in an RNN. This is also a qualitative behavior that would likely be seen with other approaches to noise regularization. So it's probably like a general thing to look out for if you are applying some kind of noise regularization to your neural network. Okay. You can also build similar looking phase diagrams for other nonlinearities. Here's the phase diagram for ReLU. I'm actually going to skip this in the interest of time. Okay, so you can also do an analysis for patch norm. I'm going to talk about this briefly, but I think it is super, super cool. So I kind of do want to mention it. Really surprisingly, it turns out that batch norm is in the chaotic phase everywhere. If you apply batch norm over and over and over again, it always induces exploding gradients and a chaotic input-output map for any nonlinearity. This likely explains why batch norm doesn't work very well in RNNs or in very deep transformers. Here we plot the predicted and actual trainable depth as a function of batch norm hyperparameters. Just as a really fun experiment, we can see the chaotic input-output map that batch norm induces by running a simple experiment with a deep linear network with batch norm. So the only nonlinearity in this network comes from batch norm. It's just like linear layer, batch norm, linear layer, batch norm, linear layer, batch norm. We take two inputs, mini batches, which consist of samples arranged in a 2D plane. However, one sample is slightly different between these two input mini batches. We can then pass both mini batches through a fully connected linear network with batch norm in each layer. And initially, for the first few layers, these mini batches remain almost identical. By depth 30, though, the batch norm nonlinearity has completely scrambled the input-output mapping, and the two mini batches are almost orthogonal and are completely decorrelated from each other. Note that the data points for both mini batches still live in a 2D plane, because for a fixed mini batch, the batch norm scaling is also fixed. And so the input-output map is always linear within the mini batch. It's just that small changes at the input resulted in the 2D planes, the two mini batches live in being nearly orthogonal. So one more mystery to describe the batch norm. It always induces chaos, which is just bizarre in deep neural networks. So we've just shown that the equivalence between wide networks and GPs allows us to both predict trainability and gain insight into properties of deep networks. Give me one moment. I seem to be losing my voice a little bit. Okay, so now let's talk about how this same equivalence allows us to perform inference with infinitely wide Bayesian networks without ever even instantiating a neural network. So, question. Okay, so the question is, how do these conclusions square with the utility of both batch norm and dropout in neural networks, e.g. ResNets? So these results about dropout destroying trainability and batch norm inducing chaos apply when they're applied many times in succession. So like each time you apply dropout, you lose a little bit of information about your inputs. And so what you want to avoid is applying dropout many times in serial. And in ResNets, what you'll do is you'll apply dropouts in the side chains, but you will not apply dropouts many times in the identity path of the network. And so you do not apply dropout many times in serial. This probably explains why dropout works in the way it is used in ResNets, but would not work if you just put it in the direct path from the input to the output. Similarly with batch norm, batch norm is super confusing actually, in ways that we're not going to get into, because it has very different properties at initialization than it has after even a few steps of training in ways that we don't fully understand. But even for batch norm, people do not apply batch norm many times in succession in the core path of a network typically. And in fact, when people train very, very deep networks, they will often replace batch norm with something like layer norm. So examples being transformers. Or they'll put batch norm in the side chain, but not in the main path, as is the case, for instance, for very deep ResNets. So once again, these problems crop up when you apply either batch norm or dropout in serial many times in a row, and which seems to be something that people avoid in practice. And this maybe motivates why. Okay, cool. So it turns out that this equivalence to a GP doesn't just hold at initialization. It also holds in general for infinitely wide Bayesian neural networks. And this allows us to do semi-magical things like make test set predictions that would come from doing inference with an infinitely wide Bayesian neural network without ever even instantiating the network. To see why, let's first look at Bayesian posterior estimation using the cartoon from the first part of the talk. So let's imagine that X star is a test point, X is a training point, and we know the network output is 1 for X. So X is our training data set in this case. This is equivalent to slicing this joint distribution along this blue z equals 1 line, where that blue line corresponds to the training label. Like we know that ZL of X has to equal 1. However, because we have 2 equivalent ways of writing the joint distribution, either as the limit of sampling from the prior or this like GP, we also have 2 equivalent ways of writing any conditional or marginal or posterior distribution derived from the joint. So for instance, one way in which we can make fully Bayesian predictions is to draw parameters from the posterior distribution over parameters given the training data, and then evaluate Z capital L for the test point for each of those parameter values. This is shown here. Here, the x-axis is the logic value for the test point, and the y-axis is the probability of observing that logic value. And the distribution over test set predictions from this posterior parameter method corresponds to the black delta functions. The other way in which we could evaluate the Bayesian posterior is just to compute in closed form the posterior distribution under the corresponding Gaussian process. This here is indicated in red. And the infinite width limit, these 2 approaches will converge to exactly the same distribution over test predictions. Saying this in a slightly different way, we're interested in the Bayesian posterior over test points. And we could either compute this by sampling parameters from their posterior and evaluating the corresponding test predictions for those parameters, as we've done in the equation on the left, Or we can compute this by short-circuiting that and just directly evaluating the distribution over test set predictions as defined by the GP in closed form. This means that if we want to evaluate the predictions of a wide Bayesian neural network, we never have to instantiate a network at all, but can just evaluate the corresponding neural network Gaussian process or NNGP instead. We formally derive this correspondence of the function space and parameter space posterior in the reference in the lower right. But informally, you can think about it just stemming from the fact that the parameter space and function space perspectives give the same joint distribution, and so they better give the same conditional distributions as well. Okay, so we just discussed how infinite width Bayesian neural networks correspond to a Gaussian process, and how this provides insight into the behavior of different architectures and makes it possible to predict when they will be trainable. I'm actually maybe going to pause here for like for 10 or 15 seconds before we move on to another square. The next sections will be much shorter than this one was. So let me know if you have any questions. Okay, cool. Continuing on. It also turns out that in the large width limit, neural networks trained by gradient descent also become really just surprisingly simple objects. Specifically, sufficiently wide neural networks turn out to behave as linear models around their initialization throughout gradient descent training. In parameter space, this means that the model can be replaced by its first order Taylor approximation. And in function space, this means that the predictions of the model become the same as those from a kernel machine. You can maybe think of the NTK neural tangent kernel square in the lower right as being a combination of the NNGP, the square in the upper right, and the linearization conditions in the lower left. The neural tangent kernel perspective on neural networks describes the distribution that results when linear training dynamics act on initial samples from a neural network that jointly form a Gaussian. So there's a question here: would sampling the WMB from other distributions and normals change the GP behavior? The answer is so definitely on a technical level, the answer is yes. The answer is it depends. If the parameters are Gaussian, then it's very, very easy to show that conditional distributions are Gaussian. If the parameters come from some other distribution, then you can still apply a central limit theorem style argument and say that for very wide layers, the distribution over readouts from that layer converges to a Gaussian, and so the network converges to a GP. So you can make similar arguments for non-Gaussian distribution over parameters so long as you are able to apply a central limit theorem like argument and say that in the large width limit it behaves like a Gaussian. But it's easiest to see when the parameters just start out Gaussian. Cool. Okay, so I'm going to tell you a little bit about this lower left square. I'm only going to discuss it at a high level, but I'm going to try to at least build some intuition for why and how wide neural networks become linear. So the core effect is that in the large width limit, the infinite number of units in intermediate layers each change by an infinitesimal amount over the entire course of training. And similarly, over the entire course of training, the infinite number of parameters change only infinitesimally. So the net effect of an infinite number of units changing infinitesimally throughout the whole network is that all of those infinitesimal changes sum up to produce an order 1 change in the network's output. However, because each of the units and receptive fields in the middle of the network change only infinitesimally, they can all be replaced by their first order Taylor approximation. So in the limit of infinite width, it turns out that throughout training, a network can be replaced by its linearization. That is, just looking at the equation at the bottom, the output of the neural network will correspond to its output at initialization plus its parameter gradient at initialization times the change in parameters plus a term that goes to 0 with increasing width. I should emphasize that this does not mean that deep nonlinear networks become linear networks when they get wide. Their output is still a very, very complicated nonlinear function of their inputs. It's just that throughout training, the change in the neural network's outputs is linear in the change in their parameters. This does mean that wide neural networks become equivalent to a random feature model, where those random features correspond to the gradients of the neural network with respect to the parameters. And training can be seen as learning the coefficients for each of those random features. The neural tangent kernel paper develops these same ideas, but working in function space rather than parameter space. So if you look at the functions induced by this linearization of neural networks, you find that they're described by the neural tangent kernel. Apologies. Cool. So as neural networks become wide, they act throughout training as if they're linear in their parameters. You can test this empirically. Here we tested this empirically by comparing the logic values for test and train output and the train and test loss and accuracy for a wide resonant architecture compared to the linearization of that same architecture. And we found surprisingly good experimental agreement between wide neural networks and their linearization until quite late in training. At least when training is performed using a small learning rate. We do find though that the linearized model deviates and falls behind the nonlinear model late in training, and also if you train with a very large learning rate, behaves very, very differently. There are, I should emphasize, many techniques in deep learning that break the correspondence between wide neural networks and linear networks. So I just mentioned large learning rates. L2 regularization also breaks this correspondence. We're still trying to actively work to understand these deviations. You should check out our recent catapult dynamic papers for maybe one piece of the puzzle. And I strongly recommend Greg Yag's recent paper on feature learning in infinite neural networks. infinite width networks. I think it's quite good and answers a big part of the puzzle as well. So more than just predicting how a single network will evolve through training, for MSE loss, we can solve for how the distribution over functions, the distribution over functions evolves throughout training. And so in the first part of this talk, we showed that the distribution over functions at initialization is a GP. We know how a Gaussian distribution evolves under linear dynamics, and because of this, the distribution over functions that results from GD training of wide neural networks with MSE loss is also a GP throughout training. I should emphasize, though, that this GP equivalence does not mean that gradient descent training is Bayesian. The distribution over functions you get from gradient descent training is described by a Gaussian process, but that Gaussian process does not correspond to a Bayesian posterior distribution for any well-defined prior distribution. So there's a question: do these results generalize from network trained with Adam? What about second-order methods? For Adam, the answer is definitely yes. These results basically say that the neural network behaves like a linear network within some volume of parameter space around initialization. And so as long as your training trajectory, whether your training trajectory is like SGD or Adam or another method, stays within this volume of parameter space, then the linearization results will apply. For second order methods, the answer is probably practically in most cases it applies, but the length of parameter update steps is unbounded for second order methods. So you would have to it would depend on the smallest eigenvalue of the second moment matrix that you use in a second order method. In that the step length you take in a second order optimization method scales like 1 over the smallest eigenvalue in the Hessian or the Gauss-Newton matrix or whatever Hessian approximation you're using. And so you would need to guarantee that doesn't diverge. But assuming that remains bounded, then it would also apply for second order methods. Okay. And just to share another experiment to emphasize the sometimes surprisingly good performance of these NNGP and NTK methods. Here are some results from a reverse ablation study we performed. So here we started in a base configuration where we expect finite width networks to be well described by theory. So we started with a finite width neural network trained with a very small learning rate and with no regularization and with no early stopping of training. We just trained it for a very, very long time. And we looked at 3 architectures: fully connected networks, CNNs with a linear readout on the top layer, and CNNs where you do a readout with global average pooling. And here all experiments are on CFAR 10. We then compared this network to the infinite width NTK and NNGP kernels corresponding to each of the architectures, or the predictions rather resulting from those kernels. We find that for fully connected architectures and CNNs without pooling, the infinite width neural networks do consistently better than the base configuration of finite width networks. For CNNs with average pooling, on the other hand, the finite network, perhaps surprisingly, does significantly better. For both finite and infinite width networks, performance can be dramatically improved by interventions. And most of these interventions break the correspondence between infinite and finite width networks. For instance, on the finite width side, you can train with a large learning rate or perform data augmentation or L2 regularization or use early stopping to do better. As you can see, for instance, in the rightmost column in the finite network pane, this causes finite networks to do far better. I think it will be really interesting as we keep on pushing forward to see how far kernel methods can also be improved as we develop analogous techniques that improve their performance. As part of the same study, from that last slide, we also found that predictions of infinitely wide Bayesian neural networks, so the NNGP predictions, usually, although not always, did better in terms of test performance than predictions from the NTK, predictions from infinitely wide gradient descent trained networks. Here in these plots, for each data set and architecture, we plot the NNGP and NTK test accuracies against each other for a variety of input preprocessing techniques. Here, points above the diagonal line correspond to NNG predictions being higher accuracy than NTK predictions. And you can see that in most cases, most points, although not all, are above the diagonal line. So if you're philosophically a Bayesian, then you maybe find this plot very satisfying because it says that the Bayesian way is better at infinite width. Okay, so returning back to our high-level table, you may also notice a suggestive gap. I was going to share a sneak preview of some early work filling in this gap using results from large width limits of neural networks to efficiently draw posterior samples in parameter space. I think I'm going to just tell you about it in like 20 seconds due to time limitations, and then wrap up. So maybe just very fast, you can make a few observations which are suggestive for why it might be possible to do something interesting for large Bayesian neural networks in parameter space using these infinite width limits. So the first observation is that drawing posterior samples from Bayesian neural networks is hard. It's like so hard that it's almost never even attempted in practice. Most work that tries to work with Bayesian neural networks uses various types of like variational approximations, like very coarse variational approximations. The second observation is that if we had a linear or an affine model, then generating posterior samples would actually be extremely easy. We could do it in closed form. This is called Bayesian linear regression, and it's like very well studied. The third observation is that, as we just discussed, sufficiently wide neural networks behave a lot like affine models. And so that makes you wonder, is there any way that we can use this correspondence of wide networks to affine models to efficiently sample from Bayesian posteriors in parameter space? The answer is yes, and I'm not going to tell you about it even at the detail of the slide due to time restrictions, but check out the plot on the right where you can see super early stage work where we successfully sample from a Bayesian posterior in parameter space conditioned on 3 training data points. So I'm very excited about this, but very, very early stage still. Okay, so summary slide. I have presented to you what I believe to be a very powerful framework for theoretically analyzing neural networks. It can be applied to either Bayesian or gradient descent training of a neural network, and in either function space or parameter space. I've shown that this perspective enables us to predict how trainability depends on architecture and hyperparameters. It allows us to do semi-magical things like compute test set predictions that would come from inference with an infinitely wide neural network without ever even instantiating a neural network. It's also provided some insights into network behavior. For instance, showing that noise regularization limits trainable depth or that batch norm induces chaos in deep networks, or something I didn't really talk about, but it's provided maybe some new perspectives on the role of equivariance and weight sharing in CNNs. Finally, I very briefly showed some early results showing that we may be able to use this large width limit as well for very large Bayesian neural networks in parameter space. Also, as I mentioned at the start of the talk, we have an open source library for constructing both finite and infinite width networks. So if you're interested in reproducing some of our experiments or running experiments of your own, you should check out the neural tangents library. All right, thank you so much for listening to my talk. It was a pleasure.
Thank you very much for the talk, Jascha. So let's wait a little bit, see if anyone has any more questions. And just for the people watching, next week we'll have the catapult phase talk. So the guy Gurari will detail these differences that appear between neural networks that are trained with large learning rates and the infinite limit versions. And then the week after that, I believe we'll have a talk by Samuel Schulholz about these ordered and chaotic phases of neural networks. So yeah, we still see a lot of stuff related to this talk today. Okay, there are no more questions. So thank you very much, Jascha. And
thank you again.
Thanks everyone that watched it, and keep coming. Bye.